Okay, do you have your highlighters out? All right, so we're going to highlight that we're doing temperature and pressure today. It's called Gay-Lussac's law. Okay, so this is going to be relating temperature and pressure. So now we have a rigid container. Volume is not changing here. So I always tell students, think about an aerosol can, a hairspray can, a can of spray paint, something like that. You have a rigid container that cannot expand. If I throw that aerosol can into a bonfire, what's going to happen? It's going to explode. Why would this little gas is around us all the time, why would this gas suddenly be able to have such force that it could blow up the container? It's under a lot of pressure because the particles are moving really fast and they're colliding with the walls of the container with a lot of force, and eventually they will exceed the container's ability to hold them. So as temperature increases, pressure increases. What kind of relationship is that? That is direct. So I have pressure on the y, temperature on the x-axis. You're going to get a nice straight line like that. All right, so it says a steel cylinder contains a sample of neon at a pressure of 760 torr. So write it down here. And a temperature of 25 degrees C. So I need immediately, when I see a temperature, I have to add 273 if it's Celsius. So that's going to be 298 K. What will the pressure of the neon in the cylinder, what will be the pressure of the neon if the cylinder is heated to 400 C? So again, add 273 to that, so that's going to be 673 K, as you might have in a fire. Okay. So we always start the problem with what? Which side am I going to start? With my torr or with my temperature? Why? Because we only have one of them, and that's what we're solving for. We want to know, bless you, what we're going to get. So 760 torr, and then write your variables down. My other variable is temperature, so temperature is doing what? Temperature is increasing, and therefore pressure is going to increase. That means I need to have the bigger or smaller number on the top. The bigger number on top. So 673, 298. I don't have my calculator. Okay, I got in my calculator 1,716 torr. How many significant figures can I have? 3. So I'm going to make that 1,720. Yes? Okay. And just always make sure and ask if your answer makes sense, okay? So my temperature was going up. I said my pressure was going to go up. Pressure went from 760 to like almost triple that, and that makes sense, okay? Just double check and make sure your answer made sense. Okay, the next one. A cylinder of hydrogen at 25 degrees C. Make that, add 273, so that's going to be 298 K. And a pressure of 1.50 atm. What temperature in degrees Celsius is required to bring the pressure down to 0.500 atm? Remember to line up your data table so that you have the same units above and below each other. Don't put your 0.5 over here. That's going to be confusing. Okay, so start with the single guy you have, which is the 298. Okay. Now look at my variables. The other one is pressure. Pressure is going down, so temperature must be going down also. How much is it going down? It's by a third, right? It's going from 1.5 to 0.5. All right. So we have 1.50. Oops, that's not a nice 5. 0.500. Oh, I wasn't paying attention. I'm sorry. You're right in my erasable gel pens. Y'all are so good. You caught my error. Because the temperature is going down, I need the smaller number on top. So 298. What do y'all get for your temperature in Kelvin? 99.3. Is that what you got? And that's what I got. What do I need to do to my temperature, though? Minus 273. And I get, ooh, that's cold, negative 174 degrees C. So there's no difference in how you're going to do the problems. You just have to know the relationship. Any variable with temperature is going to be direct. That's easy. The only indirect relationship we have is P and V. So that makes it super easy to know. So if I were you, like on my quiz on Friday, I would put those relationships on my paper before I even start the quiz. I'd put P and V and put my up and down arrows and so on, just so they're there if I need to go back and look at them later. But anything paired up with T is going to be direct. Okay, we're going to skip combined gas law. We'll do that tomorrow. But we're going to go on to the top of the next page, which is Avogadro's principle. Okay, so Avogadro's principle is just like blowing up a balloon. It's literally as simple as imagining yourself blowing up the balloon. Guess what? When I put more moles of gas into the container, what happens to the volume of the container? That's easy, right? Okay, so number of moles, if it's increasing, then the volume is increasing. If I let air out of the balloon, so I'm reducing the number of moles I have in there, it's going to get smaller. All right. Let's see. So I have 2 moles of nitrogen. Has a volume of 45 liters. Find the volume of 6 moles. All right. So what am I going to start the problem with? 45 liters. I've got my number of moles is increasing. Therefore, my volume should be increasing. So put the big number on top. So 45 times 6 divided by 2. I have 135 liters. How many significant figures can I have on this answer? I can only have 2, so I'm going to put approximately equals 140 liters for sig fig purposes. So your job today, I'm going to pass them out in just a second. Got a worksheet, it's a packet with a bunch of stuff. So, when you look at this packet, you're going to complete Boyle's Law, Charles' Law. They're all like named here. Charles' Law. So Boyle's Law, Charles' Law, Gay-Lussac's. You don't have to.
Is it going to be on the test? Okay.
And then the last one is the one we just did. They call it moles and volume or something like that. They don't call it Avogadro's. And volume law, this one. Okay, I've got a key for these. Let me stop my recording.